So thank you. Just first question, who of you worked with Celery? Okay, I see like 50%. Nice. So welcome to this talk. And this talk will be about Selinon and about distributed computing and basically how we enhanced Celery. Before I start, let me introduce myself. So as stated, my name is Fridolín. I live in Brno, Czech Republic. I used to be a reverse engineer. Then I moved to Red Hat. Now I'm in a team that is called AICOE, that stands for Artificial Intelligence Center of Excellence. And we do machine learning, big data processing, and we do, for example, optimization of software stacks. So we optimize TensorFlow and stuff like that. So I worked during my career on, for example, AFK TLS, that is an in-kernel module that allows you to transfer TLS or DTLS. Or use TLS and DTLS protocols directly inside Linux kernel. I worked on this project, Selinon, and now I'm working on project TOT, that is optimizing applications and machine learning applications. Now Selinon is more like a free time activity for me, so I will show you how it works. Okay, so first let's start with distributed computing. So in distributed computing, we have something that is called message. And this message basically describes what should be computed. It doesn't state how it should be computed, so it carries information like send an email to every participant of this talk. This message is then queued on a message broker, and the main aim of message broker is basically queue these messages. So these messages arrive and they are queued on message broker. Then we have workers that are connected to message broker, and basically these workers wait for messages, and if there is a worker available for computation, it simply picks a message and starts computing it. Meanwhile, there are queued more and more messages, so if there is a new or available worker, it simply picks it and starts processing it. If you would like to store results of what's been computing, you need to have something that is called result backend. And simply when a worker computes results, these results are stored into result backend. And so applies also for worker 1 when it finishes computation. Basically, this whole architecture is like very high level overview of Celery. And this terminology was brought by Celery. So there is result backend, message broker, workers. Celery is quite popular project, and I think it's one of the biggest Python projects out there. It's quite a large community around it, and it's basically implementation of a distributed task queue. You can find it used on many places. For example, Django uses Celery for background tasks. Okay, so now let's try to do something like task flows. In many cases, you don't have only one task that should be accomplished, but you have rather many tasks that you would like to run. And these tasks have data or time dependencies between them. That means that you would like to execute some tasks first and then run subsequent tasks. In this example, we have task 1 to task 6, and there are dependencies between them. These dependencies could be either data dependencies, so in order to execute task 5, you need, for example, results of task 1 being available, or you can have some time dependencies, meaning you are relying on some remote REST API, and you need to first query that REST API in order to proceed, because there is some background work going on. What we could do, we could create one giant like master task and put every single task into this task and execute it as one unit. The main downside thought is that if you execute all of them, which one should be like first executed? Then if some fails, how do you want to recover from these failures? And if you execute it in one worker, you don't have basically this parallelism, and you are relying on CPU parallelism or thread parallelism that we would like to avoid when using cluster parallelism. So we can utilize something that is called Celery primitives, and these Celery primitives basically allow you to run tasks in parallel. So you can state, I would like to run 3 tasks in parallel, or they allow you to chain tasks, so you execute one task after another. So let's use these Celery primitives. This was our flow design, and when we will use these primitives, we introduce something that could be called phases. So first we introduce phase 1, and we run task 1 to task 4 all in parallel. And once this phase 1 finishes, we execute the subsequent phase, phase 2, and then there can be run task 5 and task 6 in parallel. Initially, at Red Hat, when we used Celery, we used this approach, and there are a couple of downsides. If you would like to introduce a new task that has new dependencies, so imagine we would like to introduce task 7 that has dependencies on task 2 and task 6, then you'll need to somehow restructure your flow. It's important to state that Celery has everything written down in code. So basically, these phases are directly Python code that is written. And if you would like to introduce task 7, that means that you need to somehow restructure it, possibly create phase 3 and put task 7 into phase 3, or you would like to create something like phase 1.5 and execute task 7 before task 5, and stuff like that. There are also other issues, and another issue is timing. So in the real world, these tasks have different execution time, and for example, in this case, task 3 takes 30 minutes to accomplish in phase 1, whereas task 1, task 2, and task 4 all finish in 1 minute in this scenario. So task 3 basically blocks whole phase 1, and we cannot proceed to phase 2, and we get results in 40 minutes, whereas we could get results of task 6 in 2 minutes in good conditions. Okay, so these are all the pitfalls that I stated. So we were not able to add new tasks into workflow management. It was not straightforward. When a new colleague came, it was basically a nightmare to introduce him into the workflow management we had. And we then came with issues like, okay, what if one task fails? How should we recover? Celery has some features for that, but it was not that straightforward to use. And we would like to also reuse some tasks. So when we define some task flow, we would like to say, okay, I would like to run only some particular task, and everything else should be somehow find out what should be run. And over time, we find out that our data have different structures. So for some scenarios, we would like to use Postgres when we have relational data. For some scenarios where we have graph data or data that construct graphs, and we would like to explore them, we would like to use, for example, Janus graph. And it was not that straightforward into the existing Celery solution. So everything was kind of a mess. That's why we introduced Selinon. So Selinon means means celery in Greek. And basically the main idea of Selinon is to separate task logic into or configuration into YAML files. So you have simply YAML files that state how your task flow or bulk flow should look like. And then you have Python code with very small units describing how you would like to compute these results. And then you have other primitives like graph adapters and stuff like that. So let me show you. So in Selinon, there is a primitive task similar to the Celery one. And if you would like to create a task, you simply derive from Selinon task that implements a simple interface. And this task has one entry point that is called run method, and it accepts arguments that are node args. These arguments can be dictionary, or it can be an array, or anything that can be serialized on your message broker. In this example, we have a very simple task that basically multiplies, I guess, integers a and b and return them as a result in JSON. As you can see, there is nothing with storage or how you store data. You simply define how you compute data and you return results. Then, once you have this implementation ready, you create a YAML configuration file. And in this YAML configuration file, in the task section, you register your task. So you state its name and from where it should be imported. In the next section, that is called flow definitions, you state or you describe how your flow should look like. So in this example, we have flow that is named flow 1, and then you describe edges that basically state transitions between tasks. So we start with task 1 because task 1 has no source dependency. And from task 1, we continue to task 2 and task 3. And task 2 and task 3 are both executed in parallel depending on available resources in the cluster. You might be wondering, okay, what are these octagons that are shown on the picture? By the way, this picture is directly generated by Selinon. So when you describe declaratively how your flow should look like, you can use Selinon then to visualize this flow. And here you can see these octagons that are automatically injected by Selinon in this case. So what are these octagons? These octagons are conditions. Selinon allows you to conditionally execute or conditionally fire some edge in your task flow. So if we have edge that starts with task 1 and continues to task 2 and task 3, we can say that we would like to run task 2 and task 3 under certain conditions. These conditions can be, for example, results of data. So you can examine what was the result of task 1, or can be some external event, or can be based on environment variable as shown in the example here. Basically, these conditions are Python functions. You can register your own, and you can directly use them in the YAML configuration. So in this case, we proceed from task 1 to task 2 and task 3 in our flow when there is key proceed with value yes, and or if there is environment variable that is set named testing. These conditions can become compound using Boolean operators as desired, so you can do and or not. If we visualize our flow, we can see something like this. So task 1 is executed, and then task 2 and task 3 both run in parallel if the given condition is met. Okay, you might be wondering, okay, we executed task 1, but where were these results stored that were computed by task 1? And the answer is data storage or databases. So in order to use databases in Selinon, there is an abstraction that is called data storage. It's a class, abstract class that defines what methods you need to implement in order to use some storage. So in this case, we are implementing a Redis adapter. And this Redis adapter, in order to use this Redis adapter, we need to define how to connect, how to retrieve, and how to store results. By the way, Selinon comes with a pack of storage adapters. So you can directly use, for example, Redis, MongoDB, Amazon S3, or I don't know, Postgres that is also supported. Once we implement this adapter, then we state it into the YAML configuration file under the storages section. So we state name of the adapter, from where it should be imported, from which package or Python module, and then you state configuration. This configuration is basically how to connect to database. So in case of PostgreSQL, you define connection string. Then when you have tasks, you basically assign these storages to tasks. So our task 1 uses PostgreSQL, and Redis is used by task 2. Okay, nothing is perfect, and from time to time a task can fail, and we want to recover from these failures. For this, Selinon offers fallback tasks or fallback flows. So what does it mean? Basically, in your YAML configuration section, you can state something that is called failures. And these failures state what task or what flow should be run in case of failures. So in this example, we run fallback 1 if task 2 and task 3 fail at the same time. Or we run fallback 2 if only task 2 fails. You might be wondering, okay, what about time dependencies. So what if task 2 fails and task 3 is still running? So in this case, Selinon waits for task 3, and if it finishes successfully, then there is run fallback 2, and if it fails, then there is run fallback 1. It's important. Okay. So if we visualize it, we can see something like that. You can see these red arrows that basically state these fallback scenarios or error scenarios in case of task failures. It's important to state that these fallback tasks and fallback flows are tasks or flows as any others. So it's basically a task implementation. With new Selinon, you can also apply conditions. So these edges have also conditions. So meaning a fallback task or fallback flow is executed conditionally as in the main flow. I stated something like subflows or fallback flows. So what does it mean? Basically, Selinon does not strongly distinguish between tasks and flows. So they share namespace. And if you define a flow, it can become a node in graph. So in this example, there is a run init task, and after init task finishes, then there is executed flow 1. So there are executed all the tasks and all the flows that are defined in flow 1. After flow 1 finishes, then there is continue. So we continue to task 2, and you can basically nest flows as desired. You can even recursively call flows and stuff like that. Okay, so this was like very brief overview what Selinon offers, and you might be wondering how does Selinon works. So the key idea is in a dispatcher task, or you can call it also scheduler. And this dispatcher is periodically scheduled on nodes in the cluster, and it basically checks which tasks have finished, which tasks should be scheduled based on state in the flow. So in this example, we have this simple flow that starts with task 1 and task 2, and once task 1 and task 2 finish at the same time or finish, we run task 3. Imagine we decided to run this flow, so at time 0, there is scheduled dispatcher task, and this dispatcher task knows, okay, there was no task run in this flow, so it basically schedules task 1 and task 2, and it reschedules itself in 5 seconds, for example. After 5 seconds, it finds out, okay, task 1 and task 2 haven't finished yet, so it reschedules again after 5 seconds. Meanwhile, task 1 finishes. So after 10 seconds, dispatcher knows, okay, task 1 has finished, but I cannot schedule task 3 because task 2 hasn't finished yet. So it reschedules itself after another 5 seconds. Meanwhile, task 2 finishes, and after 15 seconds, when dispatcher task is scheduled, it knows that it can schedule task 3 because both task 2 and task 1 succeeded, and reschedules itself in another 5 seconds. It reschedules itself because there can be failure with task 3, and in that case, it should know that, okay, there is a failure, and there is no failure path or fallback defined in this flow. So what dispatcher does, it basically propagates this failure to parent subflows if there are any. There are also other features. So for example, you can use distributed caches. These distributed caches are used to optimize network traffic inside your cluster. You can also apply something like task and flow throttling. So when you decide, I would like to execute this particular task no more than twice a minute, you can do so with Selinon. This also applies for flows, so you can throttle wall flows. And this is especially helpful when you are relying on some remote API, and this remote API is not capable of serving your requests. Then you can do something in reverse, so you can do also task prioritization. There is also optimization of dispatcher scheduling, so you don't need to schedule a dispatcher each 5 seconds, but you can decide, okay, I would like to schedule dispatcher after 10 seconds. These are more optimization techniques. Then Selinon comes with trace points, and these trace points are some events in the cluster that you might be interested in. For example, a task has started, task has failed, task has finished, a new flow has been started, also ID of that flow, and stuff like that. If you log cluster logs into, for example, elastic-log/Kibana stack, then this is especially helpful when you would like to debug what went wrong with some flow and stuff like that. Then there are migrations. I will talk about them briefly, and selective task flows. I will talk about them as well. Okay, so what are migrations? Imagine you have a system running in production, and then you decide, okay, I don't want to run task 3 or flow 1 after init task, but I would rather switch it to task 3. But I have already running a system. So in this case, Selinon comes with migrations, and these migrations help you to basically change behavior of a production system on runtime. So Selinon automatically computes what should be executed next on configuration change. There is something called tainted flows, and the term means if you are running in production and imagine this flow 2 was already executed, or or init task in flow 2 was already executed, and you change behavior of this flow. In this case, you can state how the flow should behave, and you can choose from 3 options. Either you want to retry the whole flow, this tainted flow, that would behave differently with the old configuration in comparison to the new one, or you would like to ignore it completely, or you want to mark that flow as failed, so you probably aggregate these failed flows. Then there is another feature that is called selective task runs, and we found it especially helpful when we were executing flows periodically. So in one task, we aggregated some data from GitHub, and we wanted to refresh this data every, for example, 5 days. So in that case, we just wanted to state run only task 7, for example, and we don't care about other tasks. What Selinon does for you, it computes all the dependencies in the flow, so it knows, okay, in this flow, in order to run task 7, I need to run task 2 and task 6. And in order to run task 6, I need to run task 3 and task 4 as well. So it basically captures these dependencies and executes these tasks for you. The only thing you state is run task 7, so you don't mind about the internal structure of flow. Besides that, Selinon can be configured in a way that it reuses all the results of some tasks. So if task 3 and tasks 4 do not change over time, the results of these tasks do not change over time, you can say, okay, I would like to use all the results of these tasks, and Selinon automatically picks them from database or storage you assigned to these tasks. So Selinon is built on top of Celery. The main idea is creating a YAML configuration file that states how your cluster should behave, and then you write your Python code in which you state how you would like to accomplish or compute certain results. And if you think about it like more high level, you can have YAML configuration of your cluster, like Kubernetes cluster or OpenShift cluster, where you state what should be deployed, how it should be deployed. Then you have YAML configuration files where you state how your workflow should be done. And then you have Python logic that is basically code that you compute. Selinon offers you these conditional task executions, and this makes the flow dynamic. So it means it can behave differently over time. You can group tasks into flows, and you can create nested flows. You can even create cyclic graphs. As far as I know, Selinon is the open source tool that allows you to create cyclic graphs and cyclic flows. So you can nest them, you can create cycles, and things might get pretty crazy. Then you have this advanced task flow, failure handling, and fallbacks. And you can also do system diagnostics, and if you do aggregated logging, as stated before, Selinon can help you. Besides that, Selinon offers integration with Sentry. So if you use Sentry for monitoring, Selinon can directly send error reports into Sentry. We successfully used Selinon in a project that is called OpenShift.io. We use Selinon on other parts in Red Hat internally for workflow management. And I think, or it's used by others. It's open source. The funny part is that I didn't know that it's used elsewhere unless I released a buggy version. Then people started to complain, hey, this doesn't work. But until then, I didn't know that it was used elsewhere. These are examples of flows that we run inside Red Hat. And these are basically pretty crazy flows that nest into each other. And it's very easy for newcomers to introduce them into the system, show them YAML configuration file, and they can directly navigate and contribute to your project. Then I have prepared a demo. I had one issue with connection, so let me connect to my mobile phone. If it works. Okay. Meanwhile, I would like to thank to European Union because I'm doing on data, so it's not that expensive demo. So you can find Selinon on GitHub. It's open source. It's free. Here you can find Selinon itself. And there is a demo deployment that is deployment into OpenShift cluster. And there is a worker implementation. So worker is a Python code that states some tasks. Then there are implemented some storages. Then there is configuration files. So here are nodes. You can structure your configuration files into multiple YAML files. So in this file, you can see all the tasks that are defined in the system. So we have, for example, hello task, Travis active repos tasks, and there are additional configuration options that can be found in the documentation. Then there is a list of flows, and there are defined some storages or storage adapters. So there is in-memory, Redis, and stuff like that. Then there is flows section under Travis logs. You can find a flow that is called Travis org logs and other flows as well. So let me show you what we will demo. So Selinon uses Travis CI for testing if everything is working correctly. And here you can see that it's tested against Python 3.4, 3.5, 3.6, 3.7. And in each case or job, you can find some output, like what went, if everything is correct. I deployed this demo into an OpenShift cluster. Hopefully we will be able to load them. So I will show you the infrastructure. We have some API server that will allow us to communicate or run flows. Then we have a worker. Then we have worker dispatcher. It's kind of optimization. We found out that if we schedule tasks on a separate worker, or we schedule this dispatcher task on a separate worker, we get much better performance, and we leave computational tasks on a separate worker. Then we have a message broker that in this case is Rabbitmq, and then we have some storages that in this case is Minio and Redis. Minio is open source alternative for AWS. If we take a look at flows that are defined, so in these flows we will aggregate logs from these Travis runs. So first we will have one flow that is called Travis organization logs, and it basically checks API of Travis for active repositories, for repositories that are used in Travis CI in Selinon organization, and then for each of these repositories we will run another subflow that is called Travis repo logs. You might be wondering, okay, what is this for each? That's basically a way how you describe how many flows you would like to run in parallel, but you don't know number of flows that should be executed. Then for each repository, you check these builds that are available, and for each build, so if it is Python 3.4, Python 3.5, for each of these builds, you basically aggregate logs and store them in Travis logs storage. You can see that these tasks have different storages assigned. So here we have Redis, and here we have Travis log storage that is in fact our Minio or S3 alternative. So when we access API, so we can access it using this URL, and here we can see exposed endpoints. These are more like low-level endpoints that will show you all the flows that are registered inside the cluster. Or you can use run flow, that is some kind of low level that just puts the given message with the given flow on queue. But more important ones are these Travis CI endpoints. So here we can say aggregate all logs in the Selinon organization on GitHub, or we can say aggregate all logs for Selinon organization on GitHub, but for repo Selinon. In fact, this flow is run by the upper one, so we can run this one. So this is how our message broker looks like. You can see that there are no messages queued. Now we run this flow, so it responds, the API server responds with some response. Here you can find ID, that is a unique ID generated for the given flow. And once our Rabbitmq refreshes, so we should be able to see some messages queued. Yeah, I'm running data, so nothing. This is the issue with online demos. So what's going on? Here you can see like explosion of messages that are queued, and we can see. I see what was wrong. So we found out we were looking at some particular queue on Rabbitmq. So if we check all the available queues, you see there is 3,000 messages queued. And if we check queues, we can see separate queues for each task. So we can see, for example, that the last task that is aggregating textual representation of these logs has some number of tasks already queued. So that was the queue I was checking previously. If we refresh our minial, I'm not sure if we will see some data already computed. So let's see how the cluster behaves. So we have 6,000 messages already queued. It's important to state that the infrastructure is running on restricted, or there are not enough resources allocated. So from time to time, Redis went down because of memory issues. So here we can see some JSON files that are aggregated logs. So I can download one and show it to you. So we can go to downloads and we will wait until it's downloaded. So here you can see a JSON file that is output of our last task that aggregated for Selinon organization, Selinon repo. This is some build number from Travis CI, job, and the actual log that is the textual representation. Okay. Now, when we go to repository and we go to worker, I prepared a patch. And we found out after some time, after running in production, that some logs have some special characters that are not that well formatted inside text files. So what we did, we basically implemented a new task that is called Travis log cleanup. We registered it into our system and we assigned Travis logs storage adapter for us. And here we created migration, or Selinon did it for us, where we stated using the following command that we would like to migrate the flow that is run in the production, and that all the flows that are tainted, meaning they have some tasks in progress, should be retried. So when I merge this pull request, if I have rights, yes. And now I populate these changes to worker. So I go to worker and to builds, and I built a new worker with new configuration that is picked automatically from GitHub. On cluster overview, you can see that there is going on a build of worker. So hopefully it finishes soon. Meanwhile, are there any questions? Yes?
I'm new to... so great talk so far. What? Great talk so far. I'm rather new to Celery and Selinon, never heard of it before. Looks very interesting, and I'm wondering how the task scheduler allows you to fail over. Because if the task scheduler dies, as far as I can see it right now, no more tasks will be executed. Is there any way that you can make it a self-healing system, so to say?
So this is not an issue of Celery or Selinon, but what you would like to do is basically configure Rabbitmq to have persistence. So these tasks are nothing else, or these dispatcher tasks are described by messages. So when you publish some message, you would like to make sure that it's persisted on Rabbitmq or message broker. And once it is persisted, if message broker goes down, then you bring it up again. It basically picks the persisted task from hard disk. And if a worker goes down, basically nothing bad happens, because these workers, how they are configured, when they pick a task, start processing them, they basically tell message broker, hey, I picked this message and I'm working on it. But if it dies, meanwhile, nothing bad happens because this message is not acknowledged. So when worker finishes task, it tells message broker, hey, I finished this task, so you can throw it away. And meanwhile, no more workers pick the same message because it was marked as one worker is already working on it. And I see our build finished, so I scale up our dispatcher worker again. Meanwhile, we can check how our queues are going on. So we have still 15,000 messages queued. There is quite a lot of logs. I think it's like 4 gigabytes, and they are processed. So now our workers should start consuming these messages again. So if we check queues, you can see there is some incoming and delivered messages. And when we go to our OpenShift console and we decide, okay, we would like to run more workers, it's as simple as this. So now we have 8 workers processing tasks. We can also scale up our workers for dispatcher. So hopefully that infrastructure can hold it. And in the change, there was basically the merge change. I changed also the numbers. So after a while, we should see under directory 2 messages that are consumed with a new configuration with filtered special characters. So hopefully we will get there soon. Any other questions? If we have time.
We have 3 more minutes.
3.
3. Yes.
Oh, nice. Yes.
Thank you very much. You have the failure links that trigger another node if a node fails, but you specify those to be when that specific node fails, do this. Is it also possible to have like a global failover where if anything in the entire flow fails, trigger a node that sends me a Slack message that something went wrong, something like that?
Good question. Actually, we did something like that. And the way how we did it, it's basically you put everything into a flow and you state if that flow fails, then this is our failover task. So anything in that flow or any subflow from that flow fails, handle it. And you will receive information what went wrong, like what particular task failed with traceback. So you can basically inspect like what went wrong in the failover task.
Awesome. Thank you very much.
Thank you. How would you go about enabling or disabling a flow? Do you have to run a migration each time, or is there another way?
Run migration. Or, yes, run basically migration, where you state, I don't want to run that flow, and that's it. Any other questions?
You briefly mentioned caching of intermediate results. How does that happen?
Caching of results, you mean?
You mentioned in one of the slides, you mentioned distributed caching of intermediate results.
Mm-hmm. So this is helpful if you have, for example, Postgres, and Postgres keeps context. So for each worker that is connected, it keeps, I think, 30 megabytes of context. So it can get pretty unscalable because if you have, for example, 100 workers and each is taking 30 megabytes just to keep context, then you would like to use something like caches or optimization of network inside cluster. And how it works, you can, in the configuration, you can state, this is my cache, And cache has special methods. Cache. And before there is access the actual database, then you can specify or Selinon for you accesses this cache, and if it does not find it inside cache, then it goes to database. And it's also good that all adapters in Selinon are lazy, so they connect only when you need to have results. So it's completely fine that some worker does not connect to database because it doesn't need to be connected.
Okay, thank you. Our time is over. Thank you very much. It was a really nice talk.
Thank you.